Now, one of the reasons why we need advanced PNT, and I mentioned because of GPS, is that GPS denial or spoofing is on the rise. Now, when I first read about this, I was very concerned about what they call FUD, fear, uncertainty, and doubt, which has been a long-standing marketing method in the computer industry. I'm going to scare you into doing something right away. The security industry is really good at this, by the way. Yeah. And I said, well, GPS spoofing, who is actually spoofing GPS? Okay, this is an article from the last couple of weeks at the end of March, pointing out that within 50 miles of the Denver airport, there were significant problems with GPS because of spoofing. Spoofing means that your GPS is telling you somewhere you are not, such as over the Indian Ocean, or even worse, from here in the middle of the Rockies, right? Because your altitude really makes a difference, whether you're at the Denver airport or if you're 50 miles further to the west, right, and things like this. So this happened locally, some of these little slowdowns when you go that you may not know about. Gee, your plane is delayed. Why is your plane delayed? I'm always thinking, well, it's an engine problem, right? Well, this is happening. There's another example from last week from Tel Aviv. Tel Aviv had a 6-month high of GPS spoofing that affected commercial aircraft landing in Israel, right? Problems with, literally altitude. People think they're in the mountains, but they're not. Alarms are going off. All the way out through Cyprus. So this whole zone is being affected. And you start reading this, and the article goes, well, what's happening is Syria is sending these drones over. They're guided by GPS. The Russians have a base, in theory, in Syria. They're spoofing GPS around their base. And then it says, well, Israel also has a base, and they're spoofing GPS around there. So the point is, it's not just them that's messing us up. It's we who are messing us up to mess up them. And now this becomes a lot more serious, because it doesn't mean it's just a tactic to be used against us. It means it may be an actual working situation, which means that GPS isn't going to be reliable. It's already not that reliable when you have inclement weather, right, and things like this. So if you have the modern day version of dead reckoning with quantum, with highly accurate atomic clocks, with accelerometers, how fast are you going, atomic gyroscopes, rotations, right? Some sort of highly accurate compass, whether it's quantum or otherwise, you can tell where you are based on where you started. And that's the point. Every once in a while, you do want to resync. You hit a point to say, okay, here's your exact location. But you can go much longer. And so this will tend to be the future. Yeah, we can look out 30 years, it'll be in your cars, whatever, however many years. But this is why the military cares, this is why civilian aviation cares, right? And this is what's going to drive. So all these clocks and these sensors are going to need to be available in volume. Not just onesies or twosies, hundreds and thousands. Think of every commercial airplane that has one of these around the world. Think of every military craft, right? And so that's what's driving us from the quantum level of business, and then the photonic aspect underneath has to enable that, as we've talked about. Okay, so shifting now a little bit, again, local story. In 2001, a Nobel Prize was given to 3 physicists, including Eric Cornell at CU Boulder, for this treatment of so-called cold atoms or neutral atoms. 2 years ago, I didn't have the vaguest idea what a cold atom was, other than it's an atom that is evidently cold, right? At IBM, they still do what are called superconducting. quantum computers, and you have a freezer, basically, liquid helium, right? And you bring it down close to, so I understood cold. You know, you have a freezer, yeah, but there's no freezer here. So what you do, and this hurt my head too, is you've got your atom, and again, we're thinking things like cesium and rubidium, and there are a few others like strontium, ytterbium, which is a great name for an atom. It's the name of a town in France where they found it. What you do is you shoot lasers at it. And I'm thinking, wait a minute, you're making something cold by shooting lasers? I've seen the movies. That's not what lasers do, right? I mean, lasers make things really hot. They cut through steel, right? Well, okay, I learned more. You know, remember, I'm a math and computer science guy. I've been learning as fast as I can. But these things. But the idea is for a particular type of atom, species of atoms, that you can slow down the atom so it is in more or less a fixed position. If you imagine an atom here in one dimensions and you're shooting lasers at the right frequency at it, you can trap this atom so it's not moving left or right. And you similarly do it this way, and you do it this way, and suddenly the atom maybe is vibrating a little bit, but it's very close to absolute zero. And the analogy here is in this room, I will probably argue that before we closed the doors, this room was a little cooler, okay? And when atoms in the air, gases in the air, when it's cooler, they're moving around. They're still pretty fast, but they're just kind of moving around. But when it gets warmer, they start moving around quicker. So there's a relationship between the speed that they're moving and their temperature. So to make them colder, you slow them down. Clever. Okay. What these guys did was not only did they do this, but they showed that when you cool atoms down, groups of atoms, they actually condense into more or less, you could think of as single units, not a molecule, but single units that act as one thing and that have certain properties. They're called Bose-Einstein condensates, BECs, which I pointed out to a lot of my cold quantum people. Not everybody knows what that is, but yes, that's that Einstein, and they figured out a long, long time ago, right, that this is what happens. Think of water on a window pane, right, that's getting cooler, and the little drops, first the water appears, right, from the humidity in the air, and then this starts coming, the drops start getting bigger, right? Same things happen with atoms, and they have wonderful properties that you can do things, like sensors and atomic clocks and quantum computers. This was the heart of it. Started right up the street here. And 2001 wasn't that long ago. So this is relatively new technology here. And many different technologies. Turns out, because you can control the positioning, if you lay them out like a checkerboard, right, so flat, but atoms and squares, you can make quantum computers. Lasers are the operations, whereas we might think of doing addition, right, and multiplication and things like this. You do quantum operations via shooting lasers at these things. And the larger you can make your checkerboard, the larger you can make your quantum computer. If you put them in a ring and control them the right way, you get a gyroscope. You can make atomic clocks by putting them in layers like this, and if you put them in clouds, you can get the RF receivers. So it's a tremendously versatile type of technology, these cold atoms. And that's really critical, and that was one of the main reasons why I came.